is the roller coaster part B.1, parts 3 and 4. So we're going to continue on what we've been working on with parts 1 and 2, but now we're going to add a couple extra factors. We're going to continue with position, speed, and energy, but this time we're going to factor in the law of conservation of energy. The law of conservation of energy basically says energy can't be created or destroyed. It can only be transformed from one form to another. So I'm going to do my best not to use the terms create or destroy or is getting rid of or whatever. Instead, when we talk about kinetic energy and potential energy, we're going to say one is transformed into the other. Nothing is ever lost, it's just transformed. So energy, as we go through this setup, we're never going to lose energy. It's just going to be transformed either into motion or into energy at rest that has the potential to move. So as we go through this lab, our independent variable in this section is going to be the position of the photo gate. And what that means is the photo gate is going to move across to the roller coaster here. Along with, we are going to measure the height from the table. So we're going to see if the height from the table has a factor to play, or the height above ground has a factor to play in the speed of the marble. Okay? And so that's the dependent variable, that's what we're collecting our data on, and that's what you guys are going to be calculating, kind of the same way you did in parts 1 and 2. So the dependent variable, the speed of the marble, or the time that it's in the photo gate, completely relies on the diameter of the marble again, which is 1.9 centimeters. You guys are going to take the distance, which is the diameter of the marble, and divide it by how long the marble is breaking the photo gate. Okay? Controls, again, for this lab is going to be the diameter of the marble, the type of marble, the starting point, and the roller coaster is set at stand hole number 5. And so as we go through this lab, I just want to reiterate the importance of the law of conservation of energy. So as you start to collect your data, you'll start to see that energy is never really lost, it's just transformed into different forms. So I'm going to read you a quick section here, and then we'll do the lab. When the marble speeds up, it gains kinetic energy from falling down a hill. Kinetic energy is the energy of motion. This energy, or kinetic energy, is converted from the potential energy, the stored energy, the marble had at the top of the hill. As the marble travels, it trades potential and kinetic energy back and forth. This conservation of energy from one form to another is explained in the law of conservation of energy, which states that energy can be converted from one form to another, but not created or lost. To measure the kinetic energy, you will use the photo gate to find the speed of the marble. To calculate the potential energy, you will need to measure the height that the light beam passes through the center of the marble. So, you should measure the height from the table to the center of the hole on the light beam, and that's what I'm going to do for you guys. So on your papers or on your packets, you will get the information as I read it, and then you will also be given the times at which the marble is passing through the light beam. So for the first trial, our position 1 is going to be at 5 centimeters down the track, and at 5 centimeters down the track, the height of the photo beam is 36 centimeters. Trial number 2 is going to be at 15 centimeters, and at 15 centimeters, the photo gate is 30.5 centimeters down the track. Number 3 is 25 centimeters down the track, and the height from the table is 23.5. Okay. The next one is going to be 35 centimeters down the track, and at 35 centimeters down the track, the height from the table, the photo beam, is 17.5. Position 5 is at 45 centimeters down the track, and it is 15.5 centimeters from the table. Position 6, 55 centimeters down the track, and at 55 centimeters down the track, photo gate is 18.5 centimeters off the table. Position 7 is going to be at 65 centimeters down the track, and at 65 centimeters, it is 25.5 centimeters off the table. Position 8, 75 centimeters down the track, and at 75 centimeters down the track, it is 31 centimeters. Position 9, 85 centimeters down the track, and at 85 centimeters down the track, It is 32 centimeters. Next one. Draw 10, 95 centimeters down the track. And at 95 centimeters down the track, it is 29 centimeters above the table. Let's try that one again. One more time. There we go. Position 11, 105 centimeters down the track. And position 11, 21.5 centimeters high. And position 12, 115 centimeters down the track. And 115 centimeters down the track, it is 14.5 centimeters high. Good. And finally, we'll throw 13 in there. So that's at the bottom. It's 125 centimeters down the track. And 125 centimeters down the track, it is 11 centimeters high. Let's do that one again. There we go. All right, so what you guys are going to do is you're going to take the data that we've just collected. You are going to divide your distance or diameter of the marble by the time that it spent in the photo gate. And what you're going to see is that the speed does change. Now you're also going to plot it against the height at different positions. And when you plot it against the height at different positions, you'll start to notice a trend. That trend is going to help you better understand, or at least we'll talk about, how the law of conservation of energy is in effect. There will be a relationship between how high the marble is, or how low the marble is, and how fast it is going.